Okay, so everyone, so we are happy to have Rose as our speaker today. So Rose is an assistant professor at the University of California, San Diego, Department of Computer Science and Engineering. Her research focuses on advancing machine learning techniques for large-scale spatial-temporal data analysis with applications to sustainability, health, and physical sciences. A particular emphasis of her research is on physics-guided AI, which aims to integrate first principles with data-driven models. Among her awards, he has won Faculty Research Award from JP Morgan, Facebook, Google, Amazon, Adobe, several Best Paper Awards, and was nominated as one of the MIT Rising Stars in X. So yeah, we are very happy to have you today, and yeah, over to you.
Thank you so much for the invitation. It's an honor to give a talk here. So I'm Rose and I direct the Spatial Temporal Machine Learning Lab. So one of my passion is to advance AI for science. And let's think about like what does it mean of AI for science, right? So whenever we make a prediction using our AI algorithms, if we give this prediction to regular users, and then the way that we can convince them that our algorithms are actually working is that they will look at the predictions and ask the question, does it look good? Right? If it looks good, then they probably trust the models that we build. But then the story becomes quite different when we are making prediction for scientists. So again, AI model make a prediction, we give these predictions to scientists. So in order for the scientists to trust our predictions, they often the question of, does it satisfy conservation laws? If our prediction does satisfy conservation laws, then they would likely to trust our algorithms. So that's kind of the difference I see when we build machine learning algorithms for scientific applications. So the question is, how can we encode conservation laws or physical constraints into machine learning models such that we can convince our scientist users to use our algorithms? And that's basically the goal of physics-guided learning, right? Where we basically wanted to leverage the principles from physical sciences, combine that with ideas from machine learning. My focus specifically is about learning spatial temporal dynamics, because in physics, there has been a lot of methods that were developed to describe space-time patterns. For example, they're built on first principles. There are a lot of methods like tensor networks, differential equations, or the idea of symmetry that have been used to describe the patterns in space and time. But physics-based models tend to be rigid. They make very strong assumptions of the underlying dynamics. So sometimes they can be very far away from real-world phenomenon. On the other hand, machine learning learns from real-world data, so our models are much more realistic. We build statistical inference models, and we often take a data-driven approach. So in machine learning, we also have our own tools such as graphical models, neural networks, or deep learning, or variational Bayes, which is a type of approximate inference methods. In machine learning, we need a lot of data. And sometimes in scientific applications, obtaining data can be expensive. So that's one of the limitations of machine learning. More importantly, because machine learnings are statistical inference methods, so they don't guarantee that the predictions are physically meaningful or scientifically valid. So that's a major bottleneck of the current machine learning framework. And one of my goals is to integrate some of the principles from physical sciences, and then hopefully to inject these principles into machine learning methods, such that our machine learning methods can encode our domain knowledge as inductive bias. They can generalize to unseen domains and unseen dynamics, and then they can learn with fewer number of examples. And most importantly, they can increase our trust, especially for scientific users in artificial intelligence. So let me start by discussing this phenomenon that we observe in one of our papers at L4DC, essentially we're trying to look at this very simple prediction problem of forecasting dynamics of a sign function. So the prediction task is that we look at, essentially the left line of this vertical panel and then try to forecast into future the right portion of the sign function. So the setup is as follows, where we generate training data. We have some parameters theta, we call theta train, that is drawn from an interval A and B. And then during test, we will draw some more parameters that govern the sign function, which essentially corresponds to the initial condition and the phase parameter of the sign function, but from the same interval. Right, and this is very similar to an interpolation setting where the dynamics are actually overlapping between training and testing, as expected if we use a deep learning model such as like a sequence-to-sequence model, the predictions are perfect. However, when we slightly tweak this experimental setup, where we change the testing parameter into an extrapolation regime. So now the parameters are sampled from interval B and C, and to a deep learning model, it has never seen this kind of dynamics before. So it actually doesn't matter what model we're using. In this case, the predictions are way off from the ground truth. So this basically shows that this is a fundamental challenge of generalization in dynamics learning. It's also slightly different from generalization in the typical machine learning sense, because when we talk about generalization in the classic machine learning sense, we're saying the data distribution is different between training and testing. But then in this case of dynamics learning, the range of data distribution actually can be the same, but it just the underlying parameters that govern the dynamics are changing from training to testing. So because of this unique characteristics of generalization in dynamics learning, it creates a lot of problems for current deep learning models, and the performance will decrease significantly with test distribution or shift. And that kind of is a major bottleneck right now for learning spatial temporal dynamics in machine learning community. So one of our efforts is to think about tackling this problem from a different perspective, where we use the idea of symmetry to improve generalization. Because we think when we look at the physical dynamics, right, and because we're modeling the same type of physical system, so if the dynamics have changed from training to testing, the laws of physics do not. So if we can encode the laws of physics into deep learning models, then hopefully our deep learning model can generalize from training to testing under the change of the dynamics. So there is this kind of intricate relationship between symmetry and conservation laws given by Noether's theorem, which said that for every symmetry, there is a corresponding conservation law. For example, the translation symmetry corresponding to conservation of momentum, and the time invariant symmetry corresponding to conservation of energy. So what we want is that to build this type of symmetry as an inductive bias to improve the generalization and obtain the different nice properties that we hope for physics-guided learning. Okay, so any questions?
So Rose, can you go back to the previous slide? Michael Mahoney here.
Oh, hi, Mike.
Hi. So no, I think it was the previous one before you had another. Yeah, you had some stuff at the bottom of this slide where you were saying that there's a changing dynamic. Yeah, here, the changing dynamics. And I guess dynamics can change in sort of a lot of ways and for a lot of reasons. And when you shift to saying, well, the underlying laws of physics don't change, I mean, that's a very general statement, right? So what's the particular use case or thing that you're thinking about, right? I mean, because I can imagine the distribution system, you probably saw our stuff on changing time scales. And so that's one way that, the dynamics could change if you resolve a finer time scale. Distribution shift could just mean some minor thing changed, but that could have a big effect. I mean, it could be that you're near a bifurcation point, and so you get a big change because of some really small change. I wouldn't say any of those are obviously related to this law of physics thing,
Yeah.
So what's the examples of changing dynamics that you're struggling with that would go to justify or explain that solution? Just to
Right.
sort of
So yeah, exactly. That's a great question. So essentially, our idea is that the changing dynamics for the symmetry part is that the data distribution is the group transformation from training to testing, right? So if we can build symmetry into neural networks, that means that, this kind of changes under group transformation is actually preserved in a dynamic. So then the model knows to adapt to this kind of changes automatically. So that's actually the first part of talk. The second part of talk that I wanted to cover is saying that, if we have the same set of differential equations, but there are some parameters that are changing, right? Let's say when we work with turbulence, the underlying governing equation are, it's those equations. However, there is some external factor, let's say buoyant force, that's changing from training to testing. And if we can build symmetries in actually the latent space, right, where we know this kind of buoyancy force is time invariant, then the model can automatically adapt to this kind of changes. Does that answer your question?
Yeah, okay.
Great. Okay, so let's get right into this, right? So I mentioned the group. The idea of symmetry is built on this kind of concept of group and representation theory. So by definition, a group is a set with a composition map to itself. So an identity is an element in this group. And then for every element in this group, there's an inverse element. As an example, we can think about the special orthogonal group in 2 dimensions, which corresponding to 2D rotation. So if I don't rotate this object, that corresponding to the element 1 in this group, and if I rotate this object clockwise 60 degrees, and then the inverse operation of this group transformation is to rotate the same object counterclockwise 60 degrees. So that is an example of a group. So with the definition of a group, then we can define what we mean by symmetry. Right? So symmetry actually have 2 types of definitions. One is invariance, which means this function value is actually invariant if I apply some transformation to the input. So in other words, f of g of x is the same as f of x. So another definition is equivariance. And you can see that, in fact, invariance is a special case of equivariance, because when we allow the group representation on the right-hand side of the equation to be identity, then it reduces to invariance. Right? So equivariance means when we apply a group transformation to the input, this group transformation will automatically apply to the output of this function. In other words, f of g of x is the same as g of fx. So just to give you an example, right, let's consider the function as the scaling of the velocity field. So x is our spatial field, and this function will scale the velocity by 2. And then let's consider the group as the rotation group in 2D, which then we can represent this group as a 2x2 rotation matrix, which consists of sine and cosine elements. So when I say a function is equivariant under the group transformation, that just means when I apply some transformation, right, in this case, the rotation transformation to the velocity field, where we follow this picture, where we go bottom first, right, to the bottom left. So we first rotate the velocity field, then we apply the scaling. So we stretch the velocity field by 2. It is the same outcome as we first scale the velocity field by 2 and then rotate the entire velocity field by 45 degrees. So going through the top right route give us the same results as going from the bottom left route. So if a function satisfies this kind of condition, then we say this function is equivariant with respect to this group transformation. So when we build equivariance into deep neural network, that lead to equivariant networks. Right? Essentially, we know a neural network is a universal functional approximator. So the idea of building equivariant networks is to build this kind of functional approximator that is approximating equivariant functions. So if we think about in the simplest case, where this function consists of compositions of layers, so every layer, represent a functional mapping, right? And then this map can be seen as type of group representation. So we have a symbol here, rho, which represent the representation of the vector fields. And obviously the input and output representations are fixed because that's given by our data. However, we can do some, sort of smart things between this representation in the layers. So in the hidden layers, as well as activation functions. So we showed in the paper, which is actually not very difficult to show, is that if the layers between this neural network are equivariant, then the entire network is equivariant. If we add skip connections, which is often used in residual networks, and if it's a linear action, then it also does not affect its equivariance. So this gives us a sort of the high-level recipe of building equivariant networks, which means we need to ensure that the layers are equivariant and the skip connections are equivariant under linear actions. So the high-level idea of building equivariant layers comes from this classic model of deep neural networks, which is a convolutional neural networks. So we know a convolutional neural network is translational invariant, and the way it achieves translation invariant is through weight sharing. So let's consider this simple image in 2 dimensions where each square corresponds to 1 pixel, right? We consider the group as a translation group. So the way CNN works is that it defines this kind of filter represented by this orange block. So the weights within the orange block, which are represented as black lines, they are freely trainable. However, the weights across these 2 blocks, 2 orange blocks are shared. So if we enforce the weights to be shared across these filters, then automatically this type of neural network will be equivariant under translation. So in general, this is only dealing with the group of translation, but we can generalize this type of idea to any symmetry groups. And this condition was proved in Weiler and Sesa in 19, which says a convolutional layer is G equivariant with respect to any group if the kernel satisfies this kind of condition, which we call group invariance under conjugation. So essentially we have a kernel K of V that operates on some velocity field, and then the rho G in and rho G out is basically the representation of the group, but you can think of this as a invertible matrix. So rho in and rho out are both invertible matrix for the same group. If we apply the left and right matrix multiplication on this kernel and it does not change the output of this kernel, then we know this kernel is going to be equivariant under this group transformation. Any questions? Okay, so then the art goes into the equivariant neural networks, just boils down to how we come up with the representation of the group, right? Basically coming up with the correct invertible matrix representation of the corresponding group. So this is basically discussed in one of our iClear paper for modeling turbulence. The idea is that we wanted to develop deep surrogate models that can emulate the dynamics of a turbulence, because turbulence simulation can take a long time and we wanted to make it faster. So we know deep learning is very fast during inference, but the problem is that if we learn a surrogate model, they don't generalize when we change the dynamics slightly. So the idea here is, what if we build symmetry into deep neural networks such that it knows the symmetry in transformation in a dynamics and therefore can adapt automatically. I'm going to use the group of scaling as an example, but in our paper, we actually talked about the different type of symmetries of Navier-Stokes equations, right? So when we think about turbulence, there is this very nice property of scale equivariance or self-similarity. So when you get up in the morning and then you can see the little eddies in the coffee, whether you zoom in into the eddies, it also looks similar to the large scale turbulence of the ocean, right? So you can see there's some sort of self-similarity of the turbulence, even though they come at completely different scales. So we want to build neural networks that are scale equivariant. But standard convolution, they don't guarantee this. So we wanted to extend standard convolution to scale equivariant kernels, which requires us to share weights of the filters, not only in terms of translation, but also in terms of scales. So in this case, we must translate and scale the kernel across the different input. And that's what we did, right? And then in our paper, we looked at two sets of systems, the 2D heat equation and the 2D Navier-Stokes equations. And we know that by looking at different physical systems, they satisfy different type of symmetry. And we define the symmetry of the system as follows, which means if a solution phi is a solution of this differential system, then if I apply a group transformation to this solution, if it's also a solution of this differential system, then we say that the differential system has this kind of particular symmetry. So by this definition, we can derive different type of symmetries of heat equation and Navier-Stokes equations. Specifically, I want you to pay attention to the scaling symmetry that I'm going to talk about in this talk, where you can see that the scale symmetry of Navier-Stokes equation follows this very unique equation, where we scale the space by lambda, and then the time actually have to be scaled by lambda square. So this corresponding to this like so-called half space quarter time law in scaling of Navier-Stokes equation. And actually this law of scaling can be used to build equivariant networks that are scale equivariant. So as mentioned, what we need to do is to translate and scale the kernels at different scales, right? So we can take the 2D velocity field of a turbulence and then upscale it by different factors, which corresponding to this different size of the square that you see in the figure. So again, similar to CNN, where we share weights along different group transformations, here we share the weights across different scales. So the black line, again, corresponding to the weight of different kernel, and within each scale of the square, the weights are freely trainable. But across different scales, the weights are completely shared. And after sharing the weights across scales, we aggregate the features out as outcome of this filtering, and that becomes our scale equivariant feature representation. So in mathematically, it's defined as follows, where the scale equivariant features V of P is represented as a summation over different scales, where lambda here is a scaling coefficient. So we sum over different scales, and then for every scale, we will apply this scaling operator, which corresponds to the scaling law in Navier-Stokes equation, that's half time quarter space, half space quarter time scaling law. And then we apply this transformation to the output of the kernel, and then we share the weights across different scales. So just an example of how this can enable generalization, right? We looked at the forecasting test of ocean current. The task here is to forecast into the future the velocity field of the ocean. We're given the historical velocity field of the ocean currents. Once it's done, it can emulate the dynamics of ocean current, and then it eventually can become a component in a large-scale climate model. So here we're looking at a generalization case where we train our model on a particular scale of the ocean current, and then during testing, we perform transformation of the ocean current where we upscale the ocean current velocity field by different factor. So that's the coefficient 1 over lambda here. And the left plot shows the forecasting root mean square error, where the right plot shows a physical metrics corresponding to the energy spectrum. So it corresponding to how the frequency decays over different scales of the turbulence. So when we look at the comparison between equivariant model versus non-equivariant model, so here we're using the ResNet, and the equivariant ResNet is to use the scale equivariant kernel and replace the original kernel with our scale equivariant kernel. And you can see that when we upscale the test data by different factors, the equivariant model stay robust to this kind of scaling changes, whereas the non-equivariant model does not know about the changes from training to testing, so the error explodes in this case. Similar phenomenon can be seen in the energy spectrum era, where we guarantee the scale equivariance when we change the distribution from training to testing. Okay, so that's one example that we show that, if the changes is conforming to a particular group transformation, then building symmetry into deep neural network guarantees robust generalization from training to testing. But a lot of times in real world, this change of certain particular group transformation can be too rigid, right? Because in real world, the changes from training to testing can go much more beyond just a simple group transformation. So that's the question we want to solve in this next paper, where we are looking at a much more general case of generalization. So we're looking at this idea of meta-learning. And again, this is led by my PhD student, Ray, and my postdoc, Robin. So the idea is that we're looking at a general case of generalization. So here is the typical task that we wanted to make predictions of. So the top row shows this particular turbulence, where the turbulence is very calm, it's less turbulent. So we want to forecast the future of evolution of the velocity field. So our model is, let's say, can do very well in this top row of turbulence. Now, during testing, if we change the buoyancy force in this turbulence, now the turbulence becomes much more vibrant. Can our model still make reasonable predictions? And that's the goal of this paper, where we want to build a model that can really adapt to this kind of changes from training to testing. So we hope our model can generalize to turbulent flows of very different buoyant forces. And our idea is that even though there are different type of dynamics, but they're the same dynamical system governed by the same equations. So there must exist certain symmetrical features, in this case, a time invariant hidden features that we can discover. And then using these time invariant hidden features, we can adapt our model automatically to be able to generalize. So then we propose this type of model-based meta-learning framework, which we call dynamic adaptation network. So the key idea here is we want to infer the latent time invariant features in this dynamics, and then use the latent time invariant features to adapt our predictor. So therefore, our model consists of two components essentially. So the first, we wanted to use multitask training. So multitask training means that we will give the model a set of dynamics that are basically sampled of different buoyancy forces. So these are different dynamics that model will be learning from. And then and the second part of our model actually can cover two separate models. So one is the encoder network. And this encoder network will learn from this different type of dynamical systems and try to infer the time invariant feature. We call it time invariant disentangling. And these time invariant features essentially represent the buoyant forces that we are trying to learn from. So we enforce the encoder network to be time shift invariant. One way of enforcing this kind of symmetry is through equivariant networks. So we can enforce basically the layers in the encoder network to be time shift invariant. And on top of that, we also add a loss function through optimization to enforce symmetry. And in this case, we train the encoder network with the following loss function, where C is the weak supervision, which corresponding to the average velocity field that we can compute. So we know that buoyancy forces have some dependencies on the actual velocity field. So we use this average velocity field C to supervise the encoder network. So which means that we enforce the output prediction of the encoder network to be close to the average velocity that we compute. And the second term, and we call this a task parameter. The second term is the hidden feature that we try to infer. And you can see that we enforce that every timestamp I and j, the pairwise timestamps, they're not changing. So we enforce the hidden features to be time invariant through the second term. And then to avoid some pathological cases that all of these go to 0, we also add this regularizer to ensure that these are not pathological. Right? So So with these three terms, we train our encoder network, and then afterwards, we hope the encoder network has inferred the latent feature Z, which corresponds to the buoyancy forces. And afterwards, we will use this learned time invariant feature Z and then pass that into our forecaster network. So the forecast network before is not aware of these changes in the hidden feature, but given this latent feature Z, now we can try to adapt our forecast network accordingly. So this forecast network serves the role of adaptation. Then we can use actually two types of techniques to implement adaptation. One is instant normalization, which we call ADA-IM. So we use the latent feature Z to compute the mean and standard deviation per instance. And then we will normalize every sample using this mean and standard deviation. This actually has an important role in reshifting the distribution of the test data using the latent features. The other type of adaptation is adapt to the boundary conditions. So here we're using the latent feature Z to compute the boundaries of the velocity field. And then you can see that Z will go into a fully connected network, and this fully connected network will output some boundaries. And then we use these boundaries to pad the prediction of our forecasting network. So in some ways, we're using the latent feature to adapt to the boundary conditions of the flow. So together, right, we can adapt accordingly what is actually happening in the test data using the inferred latent features. And then in our paper, we also proved some learning theory about how this multitask training combined with adaptation can reduce essentially sample complexity of learning. So essentially we say that, using this multitask learning framework where we feed the model with different dynamic samples that different parameter regimes can actually be better than just training each task independently. And then using the shared data tightens the generalization bound of this kind of multitask training framework. And then just in terms of the performance, so here we're looking at the three different types of forecasting tasks. And the top row, we are forecasting different turbulent flows. We're forecasting the sea surface temperature, which is a benchmark data set in spatial temporal forecasting, and the ocean current data set. So here we're using the NOAA's reanalysis data. And we're looking at two types of generalization scenarios. One is to generalize to different future, which means the initial conditions are changing from training to testing. And the other type of scenario is generalization of different domains. By domain, we just mean that different buoyancy forces. So we compared with different type of meta-learning framework. So the idea of meta-learning is to train a model across different tasks, and then the model can learn to adapt for new tasks. In our case, it's just a different type of flow of a different buoyancy factor. So we're looking at ResNet, UNet, and these are just throwing all the data into this model and hope the model can learn. So these are not very strong baselines. And we also use this weaker supervision as additional signal, which tells the model this is a task that I want to make predictions for, try to use this supervision. So that's ResNet C and UNet C. And then we compared it with different meta-learning methods like MAML, and MetaNet is another model-based meta-learning framework. And our model, dynamic adaptation network DIAD, is in the bottom. So we can see that with this latent symmetry that we built in and to adapt the forecast network, we can significantly improve the forecasting performance in the generalization scenario. So for test feature, we're looking at different initial conditions. For test domain, we're looking at different parameters such as external forces. Across all the data sets, we can see that our model can generalize much better than other baselines, which shows that using this kind of adaptation network indeed can help model to generalize.
So sorry to interrupt. So
sure.
So in the previous slide, so how far into the future?
We're predicting 20 time step ahead into the future.
Okay, thanks.
Mm-hmm.
What is the time step size?
It actually varies a lot between different data sets. So I think on top of my head, I think turbulent flow, I think 10 step is 1 eddy time, and then 20 step is 2 eddies. See, for ocean current, I think it's sampled at a monthly level. But yeah, I don't have the numbers on top of my head, but they're in our paper.
Do you have more tractable problem? For instance, something that is a prototype PDE that you can time march into future, right? You know the solution rather than these ocean currents or other stuff. There are a lot of uncertainties in it. So have you tried your method to something that has time-dependent partial differential equation, for instance, that you could time march and you know the solution, you know the correct solution, and then you could say, okay, based on this past, can I see the future?
Yeah, I mean, I think we could, but I guess our goal is to say, like, if our numerical simulator are incapable of predicting evolution, right? That's where deep learning can help. So for turbulence flow, for example, it is governed by time-dependent equations. Just the simulation part of that is very expensive. If the equation is very simple, then we don't need to use deep learning. If we know the solution, we can just solve it.
I know, but how do I know that your method is actually really doing well?
But yeah,
I mean, of course, there's problems that you could do much faster. That's fine. But this is about creating a benchmark problem for your methods, right? Rather than, sea temperature, ocean currents, there's a lot of uncertainties. And in the field, there's this so-called, people call it persistence model, for instance, right? In statistics, they say the situation is going to be the same in the next 5 minutes too. So,
So yeah, because we have the ground truth, right? So in our test, we have the ground truth of the actual system, which comes from the simulator that we're using, or in the sea temperature, that's the observational data that we have. So the actual ground truth is in the data, and we're comparing our model against the ground truth. So I mean, obviously we have 0 loss. That's the best.
I mean, like Lorentz equations would be a good one.
Yeah, so the Lorentz equation is a low-dimensional system. So I think the low-dimensional system part is one for us. It's not a great advantage, right? Because when we use the common length, I think our model work well for the high-dimensional dynamics. And 2 is that the Lorentz system, it's a simulated artificial data, and I think we're using real data. I think it has more real-world impact. But I think the dynamical system, community, they like to use, Lorentz attractors or kind of Lotta-Volta type of dynamics, or Fusimo-Mokono kind of dynamics. But I think we have, our papers on L4DC and other papers, we studied this kind of dynamics before. But I just want to, I think there are great suggestions. But then for this paper, we're really focusing on like high dimensional dynamics, where we wanted to use the symmetry to show the generalization capability. Yeah. Okay, so let me show you the predictions of our model, right? So here we're trying to generalize to a very different buoyancy force. So we're comparing the predictions of our model. The first column is the ground truth, and then the right 3 columns are the predictions of our model and the baselines. So when the buoyancy force is relatively low, and you can see that it predicts this kind of turbulent phenomenon. So the closer to the target, the better, right? Then you can see that our model can capture the small scale dynamics quite well. Whereas in ResNet, because it cannot adapt, so it has some weird behavior, even though it captures the large scale dynamics well. And then for the modular based weighted meta learning method, it has some artifacts in the prediction. Another interesting aspect of our model is that because we can sample the latent space, where we can manipulate the latent space in any way we want and generate hypothetical flows. So that's basically the second row, where we actually manipulate the latent space in a way to generate very turbulent flow that the model had never seen before. And that's shown in the second row. You can see that with this hypothetical flow, we can make the flows much more vibrant, and the dynamics actually resemble the ground truth quite well. And then again, for the ResNet, it learns very blurry behavior of the dynamics. And then the modular pattern also have this artifact. All right. I guess this is basically what I want to talk about. And the idea is that we kind of inject symmetries into deep learning. And I talk two scenarios. One is to, generalization. One is generalization on the strict group transformation. The other one is more general, where we use the symmetries in the latent space. If you have questions, you can go to my website for the code, and the data is all available. Or follow me on Twitter. And here is the funding agencies that support this work. Thanks.
Okay, thank you very much for the interesting talk. So
Sure.
Any questions from the audience?
Hi, Dr. Rose. I had a question for you. By the way, it was a nice presentation, and thank
Thanks.
you. So these time invariant features where you're learning it through an encoder, I couldn't understand how you're making sure that those learned features are time invariant.
Yeah, so there are two parts that we're making this time invariant, right? One is that you see that we're using conv3D conjugated with pooling and all these layers, and all these layers are time invariant by nature. The other one is that you're training this encoder network with loss function. So you can see that Z of C, right? I means the latent feature at timestamp I of the C parameter. So we're regularizing every pair of the timestamp to be exactly the same.
Oh, I see. So if I see. So each input with respect to time has some features that are equal to each other, and you're
That's
saying
right.
that's the time invariant.
Not the feature, it's in the latent space.
Yeah,
so
right.
we feed this velocity field into this encoder network, and the encoder network will learn some latent space that's in the Z, and then we are enforcing the Z to be time invariant through this loss function.
I see. Thank you.
Mm-hmm.
Any other questions? Okay, if not, I do have a questions. So I saw that you were using convolutional layers like in the earlier part of your talk. So could you have used recurrent models instead and impose?
Yeah, I think you think that's a great question. So yes, indeed, we're using convolutional networks because they're actually very efficient. So in our previous papers, we compared, for example, LSTM convolutional LSTM based models with COM based COM networks, and then we saw that convolutional LSTM based models are much slower to train, and the performance actually are not that much better than COMNets. So that's one. From the computational perspective, we found that COMNets are much more efficient with very good performance. And two is that when we build equivariance from a theoretical perspective, it's difficult to make equivariant networks work for sequential models because of the gating mechanism. So in LSTM, there's gating mechanism, and because of that, in order to enforce equivariance, it sometimes breaks the symmetry. So in fact, there is sufficient and necessary condition which relates, equivariant networks with convolutional structure. So you actually have to have convolutional structure to be equivariant.
I see. Yeah. And also so what's the take on trying to forecast non-stationary dynamics?
Well, what's the what?
What's the take on trying to forecast non-stationary dynamics?
You mean what is the implementation, or what's the goal, or?
I mean, let's say you have stochastic process, right? You want to do forecasting. So there are stationary dynamics and non-stationary dynamics. And usually say in the geophysics community, people cares about non-stationary dynamics because that's often the case. And it seems like trying to predict non-stationary dynamics is very tough and challenging. So I was just wondering what do you think about this this problem?
I mean, we are forecasting non-station dynamics, right? Turbulence are highly non-stationary. It is difficult because we cannot guarantee the prediction performance in the long term. Could do or diverge. But I think the high-level goal is that if we can at least make short-term predictions, then we can replace existing climate models which are based on partial differential equations with deep neural networks that are faster, with decent accuracy.
How about long-term statistics?
Right. So the long-term statistics, I think that's a great comment. So in general, right? So if we just use the deep neural networks and then compute the long-term statistics, it probably will be kind of off. But there are kind of techniques that uses symmetry as a tensor network and stuff that can guarantee long-term statistics are actually similar to the ground truths. So I guess in our case, our goal is not to replace the entire climate model with deep neural networks. So we're just replace some of the short-term solvers with deep neural networks coupled with numerical solvers. So in that case, because of the the stability of numerical, I think the long-term predictions are still going to be in a reasonable accuracy range, right? Then I think the statistics in that case are relatively stable. So there's some other idea is to do like multi-scale modeling, where instead of doing small step predictions and do extrapolations, which error can propagate, we can model them at a much larger scale. So we have another paper about this, which we use multi-fidelity models, where so we have models that models at different scale, and we call it different fidelity. So the long-term prediction will be made the model a different model, then the statistics will be reasonable in that case.
I see. Okay. So any other questions from the audience?
If no one has a question, I'd like to ask if you investigated encoding or embedding physics into your encoder network to kind of like make sure that whatever you're learning is satisfying some physical laws that you know.
Like what? Like what type of physical laws?
Like the equations, the Navier-Stokes equation, for example, or the dynamical equation for oceans.
Yeah, so I guess my point of the talk, first part of the talk, is we encode physical laws in the form of symmetry, right, into deep neural networks.
Oh, so that's like I see. All right, thank you.
Okay. Yep. Go ahead.
Do you have a sense? I mean, in some cases, it seems like if you want to incorporate the constraints, say not, with a penalty method like an optimization, and not in the architecture, but with some other method, there's a whole range of methods in optimization to encode constraints instead of a hard way. I mean, in some cases, that's hard to do sort of in the usual neural network setup with forward props and back props, and in other cases it may not be. And at least the stuff I've seen on Equivariance, and so usually tries to put that into the architecture. Do you have a sense when that? I mean, in some cases, probably that's for computational reasons, just because it's a little more efficient. In some cases, it's just because it's not known how to implement it with non-penalty methods from optimization. Do you have a sense of that space and when you could implement it in other ways and it's just less efficient versus when it's not even known how to implement it in other ways?
Oh yeah, I mean, that's a brilliant question. So there is actually some correspondence between like optimization based, symmetry enforcing, right? Basically, you can actually, implement it as a regularizer to kind of constrain the weights to be somehow similar to each other and add that to the loss function. The other way is just, hard code this in the architecture design to basically link the weight, or we call it like weight tying, to make equivariance. So we have a recent paper on arXiv actually that studies this called approximate equivariant networks. I'm happy to share the link with you, but basically the idea is that we compare this different type of implementation of equivariance, right? Because if you think about hard coding this design in neural network, it's actually exact. So that's like a exact equivariance. But in practice, a lot of the dynamics don't satisfy perfect symmetry. So in our paper, we try to study, what happened if the dynamics are not perfectly symmetric. So then you need to code, kind of design your network in a special way where the weights are not hard coded. So it's partially learnable, but with some constraints. And in that case, it will actually be equivalent to just adding a regularizer to a loss function. But the problem with regularizer in a loss function is that you always have to balance the prediction loss that you want, right? And the symmetry constraint that you want to enforce. So there is kind of trade-off. It's hard to tune the parameters.
Right. So, I mean, if you were an optimization person, one way to deal with constraints is to do a penalty method and then do what you're saying. You have a regularization term. I mean, there's a whole bunch of other ways to solve hard constrained optimization problems. And so I guess, so I didn't know about your thing where you related it to the penalty method with the regularization. So I'll take a look at that. I mean, I guess, do you have a sense of if you didn't want to fall back on penalty methods from optimization, which in ML corresponds to this regularization term, but you wanted to solve it using hard constrained techniques from optimization, namely not put it in the architecture, not do a penalty method.
Right. So are you thinking about some like projection based on method?
Yeah, I mean, there's a lot of methods and it's sort of a complicated space, right? But for example, projection methods, you iterate in different ways. Yeah.
Yeah. I'm not aware of any work on the projection based method. I assume it can be like, let's say compare that with encoding weights constraint directly through design. It's a little bit more expensive, but maybe there's more efficient ways to implement these.
Okay, yeah, no, I haven't seen anything there either, and I could see that definitely interesting if you didn't want to put stuff into the architecture, but you wanted more control than with the penalty method.
Yeah, I agree.
Okay, good.
Cool. Any other questions?
Okay, so if there are no more questions, I guess we will just end the session here. And Rose, thank you very much for talking today.
Sure.
And yeah, see you next time.
Yeah, thanks for the invitation. Take care. Bye-bye.
Bye.